Right, yesterday we started working with probability, idea of probability. We looked through the idea of sample space, what it does, what a sample space is. Today we'll actually get into calculations of probability. And when we talk about probability, we're going to go with the basic stuff, and then we'll go a little bit more involved with the probability. You've dealt with some basic probabilities in your lower level mathematics. We'll get a little bit more involved in this class. Classical probability, once again, you can have a percent, decimal, or a fraction that illustrates the likelihood of an event to occur. Okay. Once again, solutions can be a percent, decimal, fraction, does not matter to me. Each event must equally likely to occur. Okay. When you talk about classical probability, each event must be equally likely to occur. And with a classical probability, it is a probability of some event occurring is equal to the number of favorable outcomes for that event times the total number of possible outcomes for an event. Favorable over total number of outcomes. Number of favorable outcomes over total number of possible outcomes. Okay, for that event. We talked about the sample space. We talked about the sample space yesterday. Example. We have a well-shuffled deck of cards. Well-shuffled deck of cards. What's the probability of drawing a heart from a probability of drawing a face card from a standard deck of well-shuffled cards? Now, we have to have a little bit of knowledge about decks of cards. And if you know a deck of cards, I'm sorry to insult your intelligence here, but there are people that I learned as we've gone along here, don't know what a deck of cards, what's in a deck of cards sometimes. So I have to explain a little bit with the deck of cards. Okay, we have suits. We have a suit. We have 4 suits. What are the 4 suits? What are the 4 suits? Hearts, diamonds, clubs, and spades. There we go. We have hearts, diamonds, clubs, and spades. Once again, I used to teach this, and I assumed everybody knew a deck of cards. That was the wrong assumption by me, because there's people that did not understand what a deck of cards, what was in a deck of cards. I grew up in the era where we didn't have phones. Okay, so when I was in college, the survival in college was you played euchre all the time, or you played hearts. You played a lot of cards when you were in college. Okay, so I knew that. But now that's not quite the case. Okay, then we have denominations in each suit. We have 4 suits. We have diamonds, hearts, spades, and clubs. In each hearts, or each one of these suits, we have denominations. We have an ace. We have a 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we have what? Jack and a queen and a king. We have a jack, queen, and king. So what we are looking here at a well-shuffled deck of cards. Okay, in this well-shuffled deck of cards, I'm going to have Coy pick a card out here. What's the probability from a standard deck of cards, well-shuffled deck of cards, him drawing a face card? Well, what do we mean by a face card? Jack, a queen, or a king. These here are face cards. Now, why do we call them a face card? Because they have faces on there. We have a jack face, a queen face, and a king face. Now, somebody bought me a deck of cards that used to play euchre in my class. Mine are Coke and all that stuff. But most decks of cards, you have faces to it. So we want to find the probability of Coy drawing a face card from a well-shuffled deck of cards. Well, we have to ask ourselves, how many face cards do we have in a deck of cards over a total number of cards? Favorable outcomes over total number of outcomes. Well, how many face cards do we have in the deck of cards? 12. Well, we have 3 in each one of these, so we have 12 face cards. That's our favorable outcomes. That's what we want over a total number of outcomes. How many cards in the deck of cards? 52. Okay, 12 out of 52. Now we look to reduce that down. Now, we want to be able to reduce fractions down. Once again, you can leave an answer there as a fraction, just need to be reduced. Decimals or percents. Now, easiest way to reduce a fraction now, because we've been there, done that many times. You've been doing that since 6th grade. If you type in to your calculator 12 divided by 52. 12 divided by 52. Hit your math button. 12 divided by 52. Don't hit enter. Hit your math button. Hit enter and then hit enter again. You have a math button on the left-hand side. Hit enter again. Hit enter twice. What it will do is it will reduce your fraction down for you. And you no longer have to do it. Three out of 13. Okay? You can think of it this way also. Each one of these suits has 13 cards. 3 of them are going to be face cards. It's going to be the same for each of them. Probability drawing. Oh, hold on. Got to draw it. Here we go. Pick a card, any card. You draw a face card. Oh, he drew the ace of spades. The ace of spades. We change that into a percent. What is that as a percent? What is that as a decimal? 23%. So we have 0.23 or 23%. Okay, once again, I would accept either of those as a solution. 23% chance of something happening. Likely, unlikely? That's sort of unlikely. Okay? But, who knows? Okay, drawing a heart from a well-shuffled standard deck of cards. Drawing a heart. What's the probability of drawing a heart? 25%. How did you come up with that? Okay, you can think of this one of 2 ways. There's 4 suits. One of them is what we want. So we can go favorable out of total number, or you can sit there and say we have 13 hearts in a deck of cards over 52. Once again, If I hit 13 divided by 52, hit your math button, hit enter, it's going to take you back to 1/4. See, Brenda's going to see if she can draw hard. There's only 25% chance of drawing hard. Just slightly better than drawing a face card. There you go. Big card, any card. Oh, she drew a diamond. You guys aren't very good today. I expect more out of you. Probability rules. Probability of an event will be between 0 and 1, inclusive. Probability of an event will be between 0 and 1, inclusive. If an event E cannot occur, its probability is 0.
Please excuse this interruption. At this time, would the seniors please report to the auditorium to meet with the Jostens representative? Thank you.
It's on Screencastify, you'll be able to pick up the rest of it. If an event E cannot occur, probability is 0. If an event is certain to occur, its probability is 1, which would translate to 100%. The sum of probabilities of all the outcomes in a sample space is equal to 1. Okay, so if a probability event cannot occur, 0% chance. You might sit there and say, what's the percent chance that we're going to have snow today in Downton, Ohio? Would there be a chance of something weird happen? So yeah, say there's a chance. Okay, 100%. If event is likely to occur, certain to occur, probability is 100%. But these are all predictions. And once again, nothing is certain to happen until it actually happens. Okay, you guys that do fantasy football and all this stuff, and they have all the predictions of what this person, the player, is going to score this week. Okay, those are all predictions. Until it actually happens, it's still a prediction. And how many times does that prediction come true? Who knows? I'll be here in 10 minutes still teaching you. I could have a heart attack and pass out and die up here. Hopefully that doesn't happen. But in 10 minutes, there's no certainty that I'm going to be here teaching you. Hope I didn't predict my own death, but we don't know until it actually happens. Okay? They're all predictions. Complement. We talk about a complement. set of outcomes not in a sample space of an event. Set of outcomes not in a sample space in an event. And the easiest way to throw or put something into a complement is throw the word not in there. So if we have some event, the event is drawing a face card from a standard deck of well-shuffled cards. What would be the complement? What would be the complement to that? If the event is drawing a face card, the complement would be what? Not drawing a face card. Not drawing a face card. Once again, we can just throw the word not in there. How we symbolize a complement. We put a little bar above it. This means the complement event. Okay? And the complement is equal to 1 minus the probability of the event. So the probability of us drawing a face card was 3 out of 13. So the probability of not drawing the face card which is a complement, is 1 minus 3 out of 13, or 10 out of 13 chance. Once again, if you're so much thinking in the mindset of I'm dealing with probability, I need to change that to a percent, go for it. 3 out of 13, 10 out of 13 is fine for a solution. But if you want to change it into a decimal, you want to change it into a percent, I will accept either of them. Empirical probability. Classical probability assumes equally likely outcomes. Empirical is based on observation of an event and the frequency of a particular outcome. Classical probability assumes equally likely outcomes. Empirical is based on observation of an event and the frequency of a particular outcome. We can still use the same basic ideas in classical, favorable outcomes over total number of outcomes. The difference with empirical probability is not each event's going to equally likely be occur. We're going to do a survey, and in that survey, we can make predictions out of that survey, but each one of the events in that survey are not equally likely to occur. We got about 2 weeks, 10 days, whatever, till the double D closes down here. Okay? We all love to go down there and get our favorite Arctic squirrels down there. Okay? Ice cream and our whatever favorite topping it is. So we're gonna do a survey here, and you're gonna tell me and tell the class what's your favorite Arctic squirrel? What is your favorite topping that you like to put in? I don't care if it is chocolate or vanilla ice cream. Whatever your favorite topping is, that's all that matters. Okay? If you like double chocolate stuff, that's fine. If you like the vanilla with the chocolate, that's fine. Just tell me what your favorite topping is when you go down to the Double D down there in Arctic and want to order an Arctic squirrel down there. Ken, we'll start with you. All right, we have cookie dough, Oreo, Reese's, cookie dough, cookie dough, cookie dough. It's like a Blizzard, okay? From the Dairy Queen. Go to Blizzard. What do you like in them? Cookie dough. All right. Cookie dough.
Chocolate. Brownie bits.
Chocolate.
Wait, what are we talking about?
What do you put in your chocolate ice cream?
Oh, like this is like toppings.
Yeah, the toppings.
Oh.
What do you like? What's your favorite?
None. I don't put anything.
You don't put anything in. You don't put anything in it. If you would like to put something in there.
I'll probably put
Oreos. All right.
turtle.
Turtle. Live turtles. Never heard of it. What's a turtle?
It's like chocolate and like nuts, I think.
Oh, okay. I didn't know if you went out there to the pond and cut up a turtle and start slicing up and putting it in there. Right? S'mores. Reese's. Cheese. Cake. Oreos. Cookie dough. Cookie dough. Eli.
I'm going cookie dough.
Cookie dough.
Cookie dough.
Cookie dough.
Turtle.
Turtle. I've never heard that before.
Cookie dough.
Cookie dough. Cookie dough. Okay, so we have a total of 5, 10, 14, 15, 16, 17, 18, 19, 20. We have a total of 20. We have a total of 20 people that were surveyed here. If Mr. Watkins walked in this door, what would be the probability? And I told him, I need you to choose somebody in this room that likes Oreos for their mix with their ice cream. What would be his probability of being able to choose somebody that likes Oreos?
3 out of 20.
3 out of 20. Once again, goes back to the idea of favorable outcomes over total number of outcomes. So we have 3 out of 20 here. Okay? Cookie dough would be 11 out of 20. That would be a pretty good chance right there. Okay? You would have 55% chance of getting somebody who likes Oreos. Okay? This here is only a 15%. This is 55%. Once again, we can calculate probabilities, but each one is not equally likely to occur. But I still go with the mindset. When we're doing probabilities, I always think favorable outcomes over total number of outcomes. What is favorable for whatever the event is over total number of outcomes? And we could put that probability for empiricals frequency in the class over total frequencies of the distribution. How many do you have? Once again, frequencies in the class. We had 11 out of 20. We had 3 out of 20. We had 2 out of 20. Frequencies of class and total frequencies in the distribution. Okay, probably the most important thing in statistics and probability. It's called the law of large numbers. The law of large numbers. It states, the more trials you have of an experiment, the closer the results will be to the expected results. The more trials you have, the better chance you have of getting what is expected.
Please excuse this interruption. As you can probably hear, the seniors should be heading back to class. At this point, please excuse the sophomores to go to the auditorium to meet with Jocelyn. Thank you.
Hey, everybody got Penny? Okay, law of large numbers, the more trials you have, the more of an experiment, the closer you're going to get to the expected results. The more, the better in the trials. The more, the better in the trials. If we would flip a coin 6 times, what would you expect if you're flipping a coin 6 times with the number of heads and number of tails? What would you expect? I'm flipping it 6 times. What would you expect? 3 heads, 3 tails. Okay, because you have a 50-50 chance in each one of these. So you'd expect 3 heads and 3 tails. So what I want you to do is flip your coin 6 times. Now, your experiment has to be the same each and every time. Okay, you want to catch it. Okay, because if it hits the table, it's going to go flying all over. You want to catch it, you want to either look at it, or you can flip it over on your hand. It does not matter. Okay, it does not matter. But do the same thing each and every time. Don't change the experiment. Count the, oh my goodness sakes, I about lost an eye on that one. Okay, count the number of heads, count the number of tails. Damn, way back. Man, that was big. I lost an eye. Yeah. Maybe we should have practiced flipping a coin here. We're checking your hand-eye coordination. So I went down to the science room and got my safety goggles out for everybody. Looking from this angle here, you don't know how humorous this is. This is brutal.
It doesn't count. That's so cool. I
Flip on it 6 times. How many heads, how many tails?
5, 2.
Oh, hold on, we'll go around the room here. Okay, we'll start with you, Kendall. Tell me how many heads, how many tails?
I have 5 heads and 1 tail.
Keep going.
4 heads and 6 tails. 4 heads, 2 tails. 4 heads, 3.
1 head, 5 tails. 4 heads, 2 tails.
Oh, 4 heads, 2 tails. 4 heads, 2 tails. 6 heads, 0.
6 heads and 0 tails. Wow, there we go.
4, 2.
4 and 2.
5 and 1.
5 and 1.
4 and 2.
4 and 2.
4 and 2.
4 and 2.
5 and 1.
5, 1.
6 tails.
0 heads, 6 tails.
2 and 4.
Oh, did I miss somebody?
2 and 4.
2 and 4. Eli?
4 and 2.
4 and 2.
3 and 3.
3 and 3.
5 and 1.
5 and 1. So if we add these up, we have 9, 17, 20, 25, 33, 43, 52, 61, 62, 63, 70, 75 heads, and 3, 4, 5, 6, 7, 10, 17, 21, 22, 23, 24, 28, 38, 39, 44, 45. Wow. We had 75 heads, 45 tails. So we have 75 out of a total of 110. We had 75 out of a total of 110. We have 45. My bad, it's 120. What is our percentage? 75 out of 120 and 45 out of 120. Say 5 divided by 120, what do we get? Anybody? What is it? 62.5. So this would be 37.5% down here. Okay, now, if we flipped 1,000 more times, and we have 500 head, 500 tail. Okay, now, we have a difference of 35 or 30 between these two. We're going to keep the difference of 30 between these two. So what we now have is 575 and 545. Out of, now we have 1,120, 1,120. Okay? So we still have a difference here of 30, like we had a difference of 30 here. And the differences are still the same. Now find your percentage. What is 575 divided by 1120? And 545 divided by 1120? What do we get now? Shout it out. What do we have?
51.3, 45.7, or 48.6.
We were at 62 and 37. Now we're at 51 and 48. We still have a difference of 30 here. But we've increased the number of trials we have. As we increase the number of trials, the closer that you will get to what is expected. We expect a 50-50. If I would add another 500 here, we'll do real quick here. 500 here, so we have 1,075 and 1,045, and divide this by 2120, 2120. Take 1075 divided by 2120. Take 1045 divided by 2120. We're still, once again, we're still 30 apart. What's our percentage now? 50.7%. and 49.3%. Getting closer and closer and closer to that 50%, even though we're still 30 off. That right there is the law of large numbers. Okay, tomorrow. I will not be here tomorrow. Okay, I will not be here. Tomorrow you'll have somebody in here. I will give you a worksheet on probabilities. Okay, you'll just work with probabilities and deal with that. We'll finish out our notes here. Also on Thursday, we'll finish out the notes. But once again, the law of large numbers, this is a classic example. Whenever you do surveys, you don't want to do surveys with just 10 people. You want to increase the number of people so you're going to get more likely outcomes. When they do drug testing, when they do the drug testing for the pharmaceutical companies, I'm still my pennies now. Even my penny. Pharmaceutical companies, their trials, when they do their trials, they do a lot of trials on their pharmaceuticals. We all watch TV and see the commercials that come on TV about drug testing or about the drugs. That this is going to cure this ailment, this is going to cure this ailment. Okay? In most chances, that's going to cure. But you may have some circumstances that occur that may not be the best. So we'll talk about more Thursday. Adios. Have a good day.